So now let's go to electromagnetic polarization. So as I move this up here, here's what we have. When electromagnetic waves interact with optical mediums. And what's an optical medium? It could be a glass, it could be a plastic. Only the electric field part of the wave interacts with the medium. The B field component does not. It's essentially inert. It's sort of like what you do when you breathe in nitrogen. So when you breathe in air, you breathe in nitrogen, but it's inert, so you breathe it back out, but your body takes in the oxygen. It's roughly the same thing. So now let's look at what I'm saying here. So now, if I have a waveform that's going along here, again, I'm being lazy and not putting my axis here. So what do I see? What I see here is that I have a wave that's going up and down like this. And this is the electric field. And then, of course, this guy's going like this. And I see I'm running out of space, so I'm going to extend this. And then my magnetic field here is going perpendicular to this. So when I'm looking at these waves, this is my B, this is my E. The only one that matters, right? The only wave that matters is going to be the wave that's the electric field. So when I look at, again, this thing, the only thing I care about is this oscillation that takes place in the electric field plane. So in this case, I'm going to say that, again, if this is my Y, this is my EY, then I only care about the wave in this plane at optical frequencies. So what do? We then replace this with a single wave. Here's my oscillating wave. And we did not write this before, so I'll spend a little bit of time writing this. So then it looks something like this. That's what's propagating. So then we could say here is that the plane of polarization is the plane where the electric field oscillates. So then we have vertically and horizontal polarization. Unfortunately, things are never that easy. It's complicated. Ordinary light bulbs produce unpolarized light. Because the hot metals inside the light bulb have numerous randomly oriented atomic oscillators. So here's sort of like an image here. And I really like this image here because what you're seeing here is that there are numerous polarizations. And you can see here that this shows here is that there's numerous polarizations. In circularly polarized light, it's only the X and the Y direction. So what we're going to do here is that we're going to simplify the picture. So we're going to simplify the picture. Because I don't want to keep drawing these numerous waves. So what we want to do here, so then we're going to look at what here? What we're going to see here is that we're going to take a front view. So if I look at a front view, what I'm going to say is that I'm going to break this down into two polarizations. So one polarization is going to have a Y component. One polarization is going to have a Z component. But I'm going to say that this can then be, we can decompose this. We can decompose this into these two waves here. So if I look at this thing, then I could say here is that the net field is then going to be the Y component in the J direction plus the Z component in the K direction, and they each have sine of kx minus omega t. So all of these can be decomposed into these two components. Now, we got to get into the misconceptions of polarizations. Okay, so this is the misconceptions about light polarization. And it turns out to be quite a big one. So let's look at this. So the first thing that we want to do is we want to talk about what is an electrical conductor. Electrical conductors allow charge to move easily through metal wires. So if you put an electric force on a charge in a conductor, it's going to move. So you could imagine that I have some wire here. Okay, so here's my wire. So now if I put in charges here, let's say that these are my little charges, these charges move very easily in wires because if I apply an electric force, they move. And this is because this is a conducting wire. That should not be a surprise. Now, let's get to the details that I want to talk about. The electric force and field are directly proportional. In other words, the electric force is proportional to the strength of the electric field. So that means here the oscillating E field of light causes electrons to oscillate back and forth. As a result, electrons collide with nuclei. Now, I should be careful when I say nuclei. I really shouldn't have said nuclei. I'm going to say with ions. So if you have a copper wire, it would be with copper ions. So the electrons collide with ions in the wires. So as a consequence, what you're seeing here is that now you have collisions that generate heat. So therefore, wave energy is dissipated as heat. And of course, as it dissipates as heat, it increases the internal energy of the wire. And then what happens here is that the wave ceases to exist and is said to be absorbed. Okay, that's an important detail. One more time. If I have an oscillating electric field of light that interacts, let's say, with the material, in this case, we talked about a conductor. What happens here is that the electrons start to oscillate back and forth, and they collide with the ions in the wires. Well, those collisions generate heat. So then they start to dissipate the wave energy as heat. As a consequence, there's no more energy in the wave and it ceases to exist, and we say it's absorbed. So here's the big deal. When vertically polarized light is incident on a vertical polarizer, the light is absorbed. That's not what textbooks say here. So again, let's look at a wave. So here's my wave now. And I'm going to send in a vertically polarized wave. So in other words, here's my wave. It's coming in like this. We know that it's moving in this direction right here. So if I look at this wave, the way we draw this wave is not like this. We draw it like this here. So this is my vertically polarized wave moving in this direction, and it's oscillating. So now what I'm going to do here is that I'm going to have a polarizer. So if I look at my polarizer, I'm then going to have a vertical polarizer. And we could imagine that this thing looks sort of like a little barbecue grill. So if it looks like a barbecue grill, what happens as the light comes in and it hits one of these, it interacts with one of these grids, what you're finding here is that no light is passed through. In other words, nothing goes through, nothing comes out. We then say that it absorbs the light. The filter absorbs the light. Note that this is just the opposite, right? This is just the opposite of mechanical polarizers. On the other hand, we could then say the exact same thing, but slightly different here. So, if a vertically polarized light is incident on a horizontal polarizer, light passes, no, I should say light is transmitted through. It's the opposite of what we've been talking about. So now, if I look at here, and I copy this guy right here, right? Here's my incident light. So now what I'm going to do here is that I need to draw a different polarizer. So when I look at the different polarizer, by the way, what I should have written over here, I should have said that the intensity is 0. So if this comes in at some intensity I naught, the intensity afterwards is 0. But now, here's what we're seeing about this other one right here. So now I have a different polarizer. This is a horizontal polarizer. And so you're seeing that the holes are now along the z direction. And so what happens now? So when this thing interacts with this guy, you could see that above the whole electric field line is in line with the electric field. So what you're seeing here is that it's taking some of it away, but not all of it. And so what happens here is that now there is light that is transmitted. It's going to get transmitted through here. So if this is some intensity 1, there is a decrease in intensity. Excuse me, the initial intensity is I naught. Afterwards, the intensity decreases. So what you find that comes out is that you transmit vertically polarized light. Again, this is just the opposite of what is shown in textbooks and websites. In fact, let's go look at that real briefly. Let me set this up. Let me get another window out. And I'm just going to type in polarization. Okay, so let me go share my screen. I just typed in polarization really quickly. And where am I at? Here we go. So here's the polarization. All I'm going to do is I'm going to click on images. Look at this one right here. Look at that. They're saying that polarized light, when you have vertical polarizers, filters out vertically polarized light. That's absolutely wrong. It's the opposite that happens. And with the little bit of 4B, which I just went through, that can't be true. Let's see, is there another one? I bet you there's tons of them. Look at this one, the same thing with this guy. Look at this. Vertical polarizer gives you vertically polarized light. That's wrong. That's absolutely incorrect. So you gotta be careful on, when you look at this thing, because it's not right. So if we were in a lab situation, I would easily be able to show you this. So here is sort of like my lab scenario. Okay, so this is a demonstration that I actually do in lab. It's part of a lab. And here's what you're seeing here. This is microwaves. And the first thing that you want to look at is that this guy right here is the purple here. This is the actual polarizer. So this is the vertical barbecue grill polarizer. Now, what you don't know, you'll have to take my word, but it's easy to check in a lab. This guy is the source of microwave. Here, let me draw this a little bit better. This guy right here, this is the microwave source of vertically polarized waves. And so when you look over here on this other side, here's what you see here. Right here is actually the detector. Okay, so this guy right here is the detector. Now, one of the things that you see here is that it's shooting out vertically polarized waves. And look at the vertical grid here. So what am I seeing here? I don't know if you could see this right here, but that reads 0. Now, if we do the exact same thing, but now we turn the grid over. And again, here's my detector, but look what it reads this time. You see that it reads max value right there. And so the way we'll start to draw these here is we're going to see this here, that if I have a vertical polarizer and it starts off with some initial intensity, the intensity after, let's call this polarizer number 1, that intensity is 0 because it filtered out the vertical components. On the other hand, this guy has some initial intensity, and see how that's horizontal? Look how I drew my horizontal polarizer. So what comes out here is that I'm going to have some intensity I1 that's not 0. And what you're going to find here is that what really happens is that the intensity in this situation is almost the same as the transmitted intensity. So, yeah, a horizontal polarizer generates vertically polarized light. A vertical polarizer by vertical polarized light generates 0 intensity. Now, note that I said it was almost approximate. So what you're seeing here is that polarizers are not ideal. So what we know here is that real polarizers are not 100% efficient at killing off polarized components. And in fact, here's what you actually see here. So here's some data on these guys. And what you're seeing here is that I have this guy here. And you could see here is that when I have the vertical polarizer has incident light that's vertically polarized, you could see right here is that this guy, this is not 100% transmitted. Oops, I said it wrong. If I have vertically polarized light on a horizontal polarizer, not all of that vertically polarized light gets through. It's approximate. And in this case, you could see that it's a little bit above 90%. So you lose 10% or so. Okay, so now let's get into the details of relative polarization. So here we go. So now we're going to talk about relative light intensity. Transmitted by polarizers. Okay, remember what we said before. Earlier, we stated that the intensity, which I'm going to define as I, is equal to the amplitude squared. Okay, amplitude squared. So how do we measure polarizers? So the angle of a polarizer is measured relative to the vertical axis. So here we go. So now if I have a vertical polarizer, let's say that this is it right here, and it has a series of slits. The way we want to draw this is not this way because that makes it complicated. We want to draw it vertically in some nice, neat vertical square like that. So this is a vertical polarizer. So when I look at this thing, this is my axis here. So if I look at this, you can see here, so if I look at this guy right here, you could see here that the angle between these two is theta is equal to 0 degrees. They're parallel. Now, if I have a horizontal polarizer, again, we don't want to draw them like big grids like this. That's too much work. We draw them as these little rectangles. And so this represents horizontal polarizer. So when I look at this angle, you could see that this angle here, that from here to here, this is theta equals to 90 degrees. Right? Or we can do something different here. Maybe we have a polarizer that looks something like this. So now if I look at my polarizer, maybe the angle is here. So when I go and I measure this, you could see that this angle comes all the way to there. And this is just going to be some arbitrary angle that we're looking at. So you could see that I'm looking at that, and that's the angle. So this is some arbitrary polarization. So now that we're going to use the standard notation, the intensity after passing through a polarizer relative to the initial intensity is what we're most interested in. So we always want to compare two intensities. So we want to compare two intensities. Let's say that we want to compare the intensity of one versus the intensity before and after a polarizer. So now let's say that I have incident light intensity. And I don't know what this light intensity is. So I'll give it some arbitrary value of I naught, and then I'm going to look at its polarization. Now remember, when I say unpolarized light, that means it has many directions. It's not circularly polarized light. But that's a lot of work to draw, so how am I going to draw it? I'm going to draw it like this. And I'm going to say that this guy has some initial intensity. Then I want to compare this to the intensity. So we're going to say we want to look at the intensity after passing through a filter or polarizer. So then afterwards, we then have a series of intensities that could be 1, 2, 3, however many polarizers we have. So let's start by looking at one polarizer. Okay, here we go. So this guy here, we're going to start off with a single polarizer. And remember, sometimes you'll hear me just say filter. And here we go. So what we can do here is that the intensity after one filter has to be 1/2. Let's draw the picture here to show you what I mean. So the intensity after passing through one filter must be half of the initial. And it makes sense because now let's think about this. So I have what? Now look how I'm going to draw this. Here's my unpolarized light, right? This has a high intensity coming in. It's unpolarized. And we know that this light is moving in this direction. So now let's say that I have a vertical polarizer here. So if I have a vertical polarizer, then I see that what's going to get absorbed is the vertical component. What's going to be transmitted along this direction here. So if this is, let's say that this is polarizer 1, what we're going to see here is that it's got to cut off half the light. So that means here that the only light that's going to be transmitted is going to be this guy right here. This intensity has decreased. So I start off with that amount of intensity. We clearly see that only half of it gets through. So therefore, the intensity of 1 has to be smaller. So what does this tell us right here? what this tells us here is that the relative intensity, so I now see here is that this intensity is going to be 1/2 the initial intensity. So then I can define the relative intensity, which is then going to be I1 over I0, and that has to be 1/2. We know what that intensity is, and that makes sense. So half of the light, it's no surprise that 50% of the light has been filtered out. In other words, the intensity of the transmitted light decreased by 50%. But it doesn't have to be just with vertical polarizers, right? So let me copy this right here. And let me just look at two other situations. So if I paste this here, and if I paste this guy over here, we can look at two other possibilities. So here I go. So what happens if I have this scenario? So now I have this guy here. How much light gets transmitted if this thing is horizontally polarized? How much light is transmitted if this has some arbitrary polarization? Well, according to what we just stated here, then this polarization has to do what? It has to go perpendicular. It's the perpendicular component that gets through here. So then this is what's transmitted right here. It's the perpendicular component. So therefore, it's this that gets transmitted right here. And in each of these situations, they all have the same relative polarization. Only half of it is taken. Only half of it. It doesn't matter the polarization here. I think I'm going to make this a little bit lighter so it's easier to see. So it does not matter. Sometimes people call that the 1/2 rule. Now, what I have here is that we're going to watch a video here in a moment, but what you're going to see here is that here are actual images of polarizers. So what I'm going to do here is that I'm going to copy my image here, and I'm going to paste this in. And it looks like this here. So what do I see here? What I see here is that in this situation, I have some initial intensity of I0 right here. So this is the light source. So when I look at this thing, what I'm seeing here is that I have unpolarized light coming in like this. And remember, it's moving in this direction. Now, look what happens when it goes through a single polarizer. So if I look at my polarizer now tells me that I have this here. So the arrow indicates the direction of the polarization. So then that means here that this is my polarizer, and this is polarizer number 1. So what is this polarizer going to do here? it's going to filter out half of the light. And I'm going to get intensity 1 right here. Now note, there's a second polarizer. And the second polarizer in red here is exactly the same as the previous polarizer. And it is also vertically polarized too. So the intensity after it comes through here is going to look like what? Well, it's almost the same size. I would say that if you look at the difference between 1 and 2, they're about the same intensity, but 1 is definitely darker. And the reason why it's darker is that if you look back up here to this picture, 10% is lost when it goes through a polarizer. Okay, and that's what you're seeing right here. Now, let's consider looking at 2 polarizers. So now we have 2 polarizers. So now we have to get into the vector nature of the electromagnetic wave. And here we go. When a polarized wave approaches a polarizer, one must account for the vector nature of the amplitude. Okay, what's happening? So here's an example. So the way we're going to consider the vector nature is that we're going to decompose one of the components. So now, here's what we go. Remember that we have unpolarized light. So let me remind you what I mean by unpolarized light. So that means I have light that's coming in. We've been drawing it with 2 directions, but it's really an infinite number of directions here. This is going to be the intensity of 1. Now what I'm going to do here is that I'm going to come in and I'm going to shoot this through a polarizer at some arbitrary angle. So it's going to look something like this here. So the light that gets transmitted is going to be perpendicular to that axis. This is polarizer 1. So now, as it continues to move forward, it's now going to interact with a second polarizer. And this polarizer is, I'm going to call 2, and I'm going to make this guy horizontally polarized for easy way of looking at this thing. So now, here I go. I have this polarized light going in here, and this has intensity 1. Okay, so once again, remember, this thing is moving in this direction. So when we look at this guy here, right? When we look at this polarizer, okay, I'm going to copy this for later use. When we look at this polarizer, we know already that I'm going to get polarization that has to be vertically polarized. We know that. The question is, what kind of intensity emerges from that? Right? So that's really what our question is. With two polarizers, we know that the transmitted light after polarizer number 2 must be vertically polarized. How much does the intensity decrease by? Is the question that we're looking at. That being the case here, what we need to do here is that we now need to go in and we have to analyze, look at the details of polarizer 2. So now, let's analyze polarizer 2 in detail. So we're going to do, instead of us, well, let's do both. So here's my side view right here. Right, here's my side view. And we know that this is horizontally polarized. And we have a wave that's incident like this. And this has intensity 1. So this is a side view right here of polarizer 2. What we want is we want a front view so that we can easily look at these guys here. So let me look at this guy here. So I'm going to do, I don't know, let's shoot for a 3x3 square. No, I think I want to make it a little bit bigger. I think 3x3 is too small. So I'm going to have 3x3. Actually, I'll keep changing this until I get it right. This seems like this would be good. And again, here's our polarizer right here. So now, what I need to do is that this polarized wave is now incident on this filter here. And what am I seeing? Here's what I see. I see the blue incident wave coming in now. And it's polarized like that. So then what I'm going to do here is I'm going to set my axis right here. And this is going to be my Y. And this is going to be my Z. So now what am I going to do? I'm going to break it up into components. So if I focus this part of the wave, this amplitude is going in that direction, and this is the Y component right there. And then this guy going in this direction, this is the Z component. Now note, what you're seeing here right away here is that the E1Z is parallel to the grid lines. That immediately tells me that E1Z is absorbed by the filter. So the only surviving component has to be E1Y. So in this case here, let me change colors here to get the angle nice and clear. This angle right here, I'm going to call that theta. Wow, that's not working very good either, is it? How about if I stick with the red? So then this angle here is theta. And you could see that E1Y is adjacent to that angle. So it has to be cosine. So if I now decompose this guy, here's what we're going to find here. So now I'm going to decompose the vector amplitude E1 into components E1y, which has E1 cosine of theta, and E1z, which will then be E1 sine of theta, but we already argued that this guy is 0 automatically. So the reason this guy, the perpendicular component, the perpendicular to the polarizer survives, and therefore it is transmitted through. In other words, the transmitted intensity is then going to be I2, and remember, this is equal to the amplitude squared, but the amplitude in this case is E1 cosine theta squared, but this is E1 squared times cosine of cosine squared. But by definition, this is, maybe I should write it here, this is the intensity 1 times cosine squared of theta. And this is between the angle 1 and 2. And this here is theta, intensity 2. So now we've calculated what that is. So then we could sort of like now summarize everything. Here we go. So now I know all the intensities, how to calculate any intensity. So here's a summary of possible outcomes. We said this. 1, if I have a single polarizer, or a filter, what do I know here? I have incident light. And it has some intensity I naught. And then I have a polarizer. Let's say that this is my polarizer right here. If it's vertically polarized, now note it doesn't matter. It's always going to cut off a half. We then see here is that the light intensity that's going to come through here comes out horizontally polarized, and this is the intensity 1. In other words, we now know that the relative intensity of a single polarizer, which is I1 over I naught, is always going to be 1/2. Okay, so now let's do the same thing with polarizer 2, two polarizers. So now here I go. This guy has now two polarizers. So what I'm going to do here is that I copied this right before, but I should have copied the whole thing. So how about if I put in just this one that we just did, and I wrote in polarizer 1, and then what you're going to see here is that I should have copied this guy as well. So this is I naught, so I'm going to copy this again. And here we go. So now what I'm going to do here is that I'm going to imagine that I have two polarizers now. And I'm going to modify this guy. And it's going to look something like this here. So this is going to be polarizer number 2. And I'm going to clean this up by doing this guy. So now if I look at this guy, I'm going to have a polarizer that's going to be arbitrary in its angle here. My computer is starting to act funky here. So now what's happening? Light comes in. I'm going to get light that's horizontally polarized. And then I'm going to have light that's now going to come out that's perpendicular. It's going to look like this, and that's going to give me my second intensity. So when I look at my relative intensity here, you could see that I'm going to pick up values here. The first one, after 1, I clearly have a half because I took out half. And then the second one here is that it's going to be cosine of theta 2 minus theta 1 squared. It's the relative angle, right? So when I look at the relative angle, it's this angle relative to these guys. So this guy, this is going to be theta 2, and in this case, this is theta 1, but in this case, it's 0. So the way I'll write this here is then I'm just going to say that this is 1/2, and then I'm going to say this is cosine squared, but then this is the angle difference between polarizer 1 and polarizer 2. Now, if I do the same thing as I did before, I'm trying to copy these things. Man, my computer is not cooperating. So now let's go to 3 polarizers. So if I do 3 polarizers, what do I see here? Well, I have 2 polarizers here. Okay, so I have my incident light coming in. Then we know that we're going to get light that goes like this. So I'm going to get horizontally polarized. And we know we get half. And then we get the vertical polarizer right here, or the arbitrary angle. And then I'm going to get light that comes like this. that comes out. But now, man, I hope this pastes right. Okay, good. So now I'll adjust this guy. And then I'm going to get rid of this. And now I'm going to get rid of these guys right here. And so what I see here is that I have another polarizer. And let me give this some arbitrary value. How about if I look at this guy that looks like this here? So this polarization, not like that. Let's say I'm going to do a different, yeah, let's do it like this. So this is this polarization. So when this light comes through, this is the light that has to be perpendicular to this. And I should have called this 3 here. So then I see that this light coming through is going to have intensity 3 like that. So now I got to look at the angles. Again, I'm comparing that angle to give me theta 1. I'm going to look at this, and this is going to give me angle theta 2. And you could see here is that this is going to give me angle 3. So then if I look at the relative intensity, what do I see here? I'm going to get a factor of what? Well, I'm going to get the factor of 1/2 as expected. Then I'm going to get a factor of cosine squared, where it's the angle difference between polarizer 1 and 2. And then to get the third factor to get the third relative intensity, this will then be cosine squared between 2 and 3. And when I say that's the relative intensity, note that this is really I3 divided by I naught. So the last thing I want to do here is that I want to come in and show you 2 more videos before we move on here. So here we are here. Let me get rid of this. So now I want to play this video for you. Here we go. It's about 2 minutes. Here we go.
Here's a single sheet of polarizer, a kind of filter that lets through only electric field vibrations that are in a certain direction called the transmission axis. I've marked the transmission axis on the polarizer with that double-headed arrow. Vibrations perpendicular to that are blocked, absorbed by the material. This polarizer is in front of a light table, and the light waves coming at you are wiggling up and down, left and right, and every diagonal direction. Those diagonal vibrations, however, can be thought of as simultaneous vertical and horizontal vibrations. So we can think of the light as having only vertical and horizontal components of vibration. And this polarizer, as it's oriented now, is letting through only the vertical vibrations. If I turn it, however, then the light getting through is now vibrating horizontally.
Note that he said that incorrectly. When you put it horizontally, it's not the horizontal that gets transmitted, it's the vertical.
Here's a second polarizer. With the 2 transmission axes parallel to each other, there's not much difference where they overlap. The first filter, closer to the light source, blocks almost all of the horizontal vibrations and lets through the vertical vibrations. The second one, closer to you, lets almost all the vertical vibration through. It would block horizontal vibrations, but there are no horizontal vibrations hitting it because they were blocked by the first polarizer. Now, if I rotate the foreground polarizer, what will happen? Let's see. The first polarizer blocks the horizontal vibrations. The second blocks the vertical vibrations. So essentially no light gets through. I say essentially because the filters are not 100% perfect. Now I'm going to put a horizontal polarizer on a stand here in the foreground. So I have a hand free to introduce a third polarizer, a small one, in between the first two. Notice that some light gets through when the small polarizer is diagonal, but no light gets through when the small polarizer is either vertical or horizontal. Can you explain why?
Okay, let's go look at this in detail with the images that he produced. So what I'm going to look at here is that I'm only going to look at two images. Okay, so what I'm going to try to do here is I'm going to copy this one. So what we just showed you here was the video polarization 3. So I want to look at two of the polarizations that were just shown in the video. I want to look at these two right here. And let's look at the details. The 3 polarizer is the one that's most interesting. So I'm going to come back and I'm going to use what polarizers that we had before. So I'm going to copy the 3 from before and spread them out. So here I go. I gotta figure out how to do this. So this one has 3 polarizers, and this one has 2 polarizers. So what I'm going to do here is that I'm going to delete this guy, and I'm going to spread these guys out a little bit to make it more clear. So here we go. So now let's go look at this. What am I seeing in this situation? So one that he had here is that we could have a combination of 2 possibilities. I'm going to choose the first combination as being vertical, and the second combination is going to be horizontal. So then I have incident light. The light that's going to get transmitted is only the horizontal component. And when I see here that I'm now going to get polarization that's along this horizontal axis, so it's going to get all completely absorbed. So when I look at this, you're seeing that this guy right here is polarizer 1. This guy right here is polarized 2. So you will always get, the polarization to cancel out like this. Now, like he said in the video, you're not going to have 100%. Now let's look at the second one. Now, in this situation, I have incident light that's coming in. And so now I got to change my polarizations as they are. So what I have here is that I'm going to insert a polarizer right into here. So what you're seeing here is that this polarizer in this situation is now horizontal. And you could see that instead of me calling it 2, I now calling it 3 here. So now what happens? I have polarization that comes through that's going to be horizontal. And then what's going to happen? It's then going to go perpendicular here. So I now have this, polarization that's going to come through here. But then what happens is that I'm now going to get vertical polarization that comes out. So even though 1 and 3 are perpendicular, a third one causes this to happen this way. So what you're seeing here is that you're seeing this situation here. So the way I've drawn it, I got to change it to make it color. So this guy right here is polarizer number 3. This guy is polarizer number 2. And then finally, this one right here is polarizer number 1. And that's how we get that. And then one last thing that I want to show you here is that rainbows can have polarization because of how the light comes out of a raindrop here. So what I want to do here is I want to go show you this video. And this is my last video. And check this polarization out. And you can see how the rainbow is being filtered out, which is pretty cool here. So now, let me go and get those images. So just give me a moment here. What I'm trying to do is I'm trying to get multiple images. So let me copy these. Okay, so let me go and insert this. And you can see here is that if I now insert these images that I just copied, they look something like this. And this is what I see here. What I'm seeing here is that rainbows have polarized light, just like the hood of your car. So then rainbow light is polarized. And you could see the variations in the intensity. And that is not surprise here because we know that the relative intensity, so if rainbow light is already polarized, then the relative intensity should be proportional to cosine squared. So that means if I look at this thing, this polarization should now look something like this here. I did not draw that very well, but that's essentially what that is looking at, where you could see here is that this guy is at 90 degrees right there, where again, this is the relative intensity right here.